Hello everyone. Today we're going to look at motion problems with fractions, but problems that have a current or wind. So let's take a look at the do now. We need to discuss a very important concept before we start looking at the word problems. A boat travels 8 miles per hour in still water. The water current is 2 miles per hour. What is the speed of the boat traveling A, downstream, B, upstream? So let's see what we mean by traveling downstream or upstream. When we travel downstream, as we see in the picture, this is downstream here, notice that the canoe is traveling with the water current. So if the canoe by itself can go 8 miles per hour and the water current goes 2 miles per hour, then when the boat travels with the current, the boat's speed would increase. So when we say downstream, it's implied that we're going in the same direction with the water, or with the water current. So that means the canoe would increase speed, and it would make sense that the speed would be 8 plus 2, or 10 miles per hour. But when we travel upstream, as this green canoe down here is doing, notice that the water current is still going in this direction, but the canoe is going in the opposite direction. So we say that the boat is traveling against the current. So in that case, it would slow the boat down. So let's just write that down. So this is against the current. And instead of adding 2 to 8, we would subtract 2 from 8. So the speed would be 6 miles per hour. So this is a very important idea. If the boat, this is the boat, is traveling in one direction and it's traveling in the same direction as the current, we say it's downstream. But if the boat is traveling in the opposite direction and the current is going the same direction, because it always goes in one direction, we say this is upstream. So downstream we add, upstream we subtract. All right, let's take a look at the next exercise. On your worksheet, I have this table. So I'd like you to take the worksheet and complete the table. Let's do the first one together. All right, so the rate of the boat in still water is 12 miles per hour. So this is 12 miles per hour. And the rate of the current is 2 miles per hour. What would be the rate of the boat downstream? Well, downstream, we're going with the current. So we add. So that would be 12 plus 2, or 14 miles per hour. Whereas the rate of the boat upstream is against the current. That would be 12 minus 2, which is 10 miles per hour. So I'd like you to fill in the chart. Pause the video and then restart it. All right, so this is what I obtained when I completed the chart. So when we go downstream, we add. When we go upstream, we subtract. So 15 plus 4 is 19. 15 minus 4 is 11. In C, 1C, 7 plus C would be the algebraic way of representing the rate of the boat downstream, and 7 minus C would be the algebraic way of representing the boat going upstream. And then here comes the key that we will be using in our motion problems, this step right here. If X is the rate of the boat in still water and C is the rate of the current, then X plus C could represent the rate of the boat downstream, and X minus C could represent the rate of the boat upstream. Now, it doesn't have to be a boat. Airplanes can fly with the wind and against the wind. And I'm sure that when you took a trip you notice that in one way, either going or coming back, the trip took a little longer. And that was probably because the plane was going against the wind. So in 2A, the rate of the plane flying with the wind would increase, that's 575. Against the wind, we subtract, that's 545. Again, in B, we would add 640 and subtract 560. C would be 570 plus W and 570 minus W. And then finally, the algebraic way, if X represents the rate of the plane in still air and W represents the rate of the wind, then X plus W would be the rate of the plane flying with the wind, and X minus W would be the rate of the plane flying against the wind. Okay, so let's summarize. So with the motion problems involving current or wind, we let X represent the rate of the boat or plane. These are the most popular ones that are used in still water or air current, or in still wind. In other words, it's just the rate of the boat of the plane going by itself. C would represent the rate of the water current or the air current or wind current. Okay. X plus C would be the general way to represent the rate of the boat or plane traveling with the water or wind current. And X minus C would represent the rate of the boat or plane traveling against the water current or wind current. Okay, and when it comes to boats or ships, we say that downstream is when we travel with the water current, and upstream is when we travel against the water current. That's all we need to remember. And we should also remember that just like the motion problems we did last time, we could say that the rate is equal to distance over time, or we could say that time is equal to distance over rate. So keeping that in mind, we're ready to go over our first motion problem with current and or wind. This is number 3 on the worksheet. It says Haley's paddle boat travels 2 kilometers per hour in still water. The boat is paddled 4 kilometers downstream in the same time it takes to go 1 kilometer upstream. What is the speed of the river? So let's just write down that let X equals, this is what we're finding, the speed of the river, which is understood to be the rate of the river current. Because the current in the river makes the water move. And now we have downstream and upstream. So we also know that distance divided by rate is equal to time. So now let's look at the distance. It does say the boat paddled 4 kilometers downstream. So we'll put the 4 here under distance, and 1 kilometer upstream, which is 1. We could represent the rate of the boat, well, the rate of the paddle boat in still water was 2 kilometers per hour. So we could say the rate of the boat traveling with the current downstream would be 2 plus x, and the rate of the boat traveling upstream would be 2 minus x. So the times traveled would be just these fractions. Downstream is 4 over 2 plus x, and upstream is 1 over 2 minus x. And now we have to relate the times. What do we know about the time? The boat is paddled 4 kilometers downstream in the same time. So the time going downstream, which is 4 over 2 plus x, is equal to the time going upstream, which is 1 over 2 minus x. And that's how we would set up the problem. And to solve such a problem, we have a proportion, so we can simply cross multiply. And we distribute. And we solve. We get 6 equals 5x, I believe. Yeah. And x is equal to 6/5. So the answer is, what is the speed of the current? The speed of the current is 1 1/5 kilometers per hour, which is equivalent to 6/5. And that would take care of our first problem. All right, this is problem number 8 on the worksheet. I'm going to change this to an 8. And it says, the Mississippi River boat can travel at the rate of 20 miles per hour in still water. To travel 72 miles downstream in a river, the ship requires 3/4 of the time that it requires to travel the same distance upstream in the same river. Find the rate of the river's current. Okay, so let's set this one up together. So we've got downstream and upstream again. X still represents the rate of the river's current. And we have distance divided by rate is equal to time. So let's take a look at that. So we know that the Mississippi showboat can travel at the rate of 21 miles per hour in still water. So we could fill in the rate downstream and upstream. So downstream, it would be 21 plus x, and upstream, it would be 21 minus x. To travel 72 miles downstream in a river, the ship requires 3/4 of the time that it requires to travel the same distance upstream. So the distance, whether going upstream or downstream, is understood to be 72. So immediately we can represent the time. Time downstream for the boat is 72 over 21 plus x. And time upstream for the boat is 72 over 21 minus x. But this time, the times are not the same. Let's write them down side by side and see how we could make them the same. Okay, we have to realize that when we travel with the river current downstream, this should take less time. But traveling upstream against the current would take more time. So we know that this quantity on the left is smaller than the quantity on the right. So we have to see what is the relationship between the times. So let's read it again. On the second line, to travel 72 miles downstream in a river, the ship requires 3/4 of the time that it requires to travel the same distance upstream the river. So it's understood that the time going downstream is 3/4 of the time going upstream. And this would be our equation to solve. That I will leave up to you. But this is how we would set up the problem. But if we did solve, I did this for you very quickly. Well, actually, I paused the the video, and then I did it here. And my answer was 3 miles per hour is the river current, just in case you wanted to check. All right, let's look at a few more. This problem is one of my favorites because it doesn't use a boat and it doesn't use a plane, but it talks about the moving sidewalks, which I'm sure you've seen in airports or maybe in Disneyland. There's a moving sidewalk at the Newark airport that moves at a speed of 1.7 feet per second. Walking on the moving sidewalk, Jamie can travel 120 feet forward in the same time it takes to travel 52 feet in the opposite direction. How fast would Jamie be walking on the non-moving sidewalk? So let's just write down, let x equal the rate Jamie walks period, which is what she would walk on a non-moving sidewalk anyhow. And we'll say that, so walking with the sidewalk in the same direction and in opposite direction, which I've never seen someone do at an airport, but I guess we wanted to make a word problem here. So we have distance divided by rate is equal to time. So if she's walking in the same direction, it says walking on the moving sidewalk, Jamie can travel 120 feet forward in the same time. So this is 120 feet. In the same time, it takes her to travel 52 feet if she walks in the opposite direction. So the rate of the sidewalk is 1.7 feet per second. So we'll say x plus 1.7 in the same direction, x minus 1.7. So the times are 120 over x plus 1.7. Here it's 120. Oh, I'm sorry, not 120. I meant 52. 52 over x minus 1.7, and it says that it's the same time. So we would make these equal and solve. Okay, so let's solve this quickly. Let's take a minute and solve it quickly. So solving this algebraically, the answer that I came out with was 4.3 feet per second. This is the rate Jamie walks. All right, let's try another one that's a little different. Okay, now I'd like you all to try number 11. Try setting that up by yourself, and we'll check in a bit. Now, this problem is a little different. It's not your conventional motion problem. It says, Katya's plane has enough fuel to fly 6 hours, and its speed in still air is 240 miles per hour. The plane departs with a 40 mile per hour tailwind and returns to the same airport flying into the same wind. Okay, so we know that the rate of the air current is 40. Let's just keep that in mind. So here we're going to add 40, and here we're going to subtract 40. And it does say that her plane travels in still air at 240 miles per hour up here. So we're going to add 240 plus 40 and 240 minus 40 for the rates with the wind and against the wind. But they're asking us, how far can Katya's plane travel under these conditions? So here, what we have to do is we're going to let that distance equal x. Okay, so assuming that she's traveling the same distance with the wind and against the wind, but her rates are different. So her time with the wind would be x over 280, and the time against the wind would be x over 200. And because the total time is 6, we would add these two, and make it equal to 6. And let's not forget the key. Let x equal how far the plane travels since it is the distance to the same airport. How far the plane travels one way to and from the airport. Okay, so this is a little different. We have to add, and to solve this, we multiply both sides by the least common denominator, and that would be 560. So if we multiply both sides by 560, let's do that. And make these equal. We can simply divide through on the side that we have to distribute. So when we distribute, this would become a 2x. Oh, 2x. And then 20 goes into 560. 28 times, so we get 28x here. Equals 560 times 6, which gives us 3,360. So we get 30x equals 3,360. We divide each side by 30, and our final answer is 112. So x is 112. So Katya's plane, oh no, actually Katya's, oh, let me just erase this. Katya's plane travels 112 miles, because they did ask us for the distance, how far it can travel under those restrictions. All right, let's look at one more. This is problem 14 on this sheet. Sophie's motorboat in still water is 3 times the speed of the river's current. A trip up the river and back takes 10 hours, and the total distance of the trip is 100 kilometers. Find the speed of the current. All right. Pause the video and try to set this one up yourself. And then when you're ready, restart the video. Okay, let's analyze this together. Now, this one's different because we don't know the speed of the water current and we don't know the speed of the motorboat. And all the other problems, we were given that information. So let's look at this again and see how we could put it together. Sophie's motorboat in still water is 3 times the speed of the river's current. So immediately we could say, let x equal the rate of the river current, and let 3x equal the rate of the motorboat. And immediately, the rate going up the river would be 3x plus x, which is 4x, and the rate down the river would be 3x minus x, which is 2x. So that was a little different. A trip up the river and back takes 10 hours, so the total time is 10. Okay, and the total distance of the trip is 100 kilometers. So for this problem, we have to represent the distance, 100 kilometers. Here, I'm afraid that we would have to here I think we would have to assume that the trip up the river and back would be the same distance. So that would be 50 each way. And that's only because she's going up the river and then back. So it's implied that it's 50. So the time going up the river would be 50 over 4x. Down the river would be 50 over 2x. And when we take those two times and add them, we get 10, I believe. All right, and there are various ways of solving this. I mean, we could divide, we could multiply both sides by 4x, or you could divide one of the 2's in here. This becomes 2, and this would become a 25. We could simplify that fraction only because we want to get a common denominator. So we get 25 over 2x plus 50 over 2x equals 10. So 25, well, that would be 75 over 2x equals 10. So 75 equals 20x, and x equals 75 over 20. And x comes out to be 3.5 when we divide. Oops, wrong thing. X equals, oh my gosh, what happened? Oh, I have the pen. Okay, x equals 3.5. So the speed of the current is 3.5 kilometers per hour. And of course, Sophie's rate would be 3 times that number with the speedboat in still water. And that takes care of our motion problems with current or wind. Have a wonderful day. Bye.